I want to explore forces at an angle, how to break them down into x and y components, and how to use those x and y components to determine things like the acceleration of an object. Let's take a look at a scenario here. A 5 kilogram object on a flat horizontal surface is pulled with a force of 40 newtons at an angle of 60 degrees. Well, let's break this problem down a little bit together. First of all, let's draw a force diagram for this object. So we have a 5 kilogram object here, and I'll fill that in as 5 kilograms, and we have a flat surface that it's at rest on, and then we have a force acting on it, and the force is 40 newtons at an angle of 60 degrees. So we have a 40 Newton force acting at an angle of 60 degrees. And I'm going to draw some lines here. And those are going to be x and y components very soon. Our question is, assuming there is no friction, what is the acceleration of this object? Let's break some stuff down here together. First of all, let's think which forces are acting on this object. We know we're on Earth on a flat horizontal surface, so we certainly have gravity. And gravity is going to act downwards on this object. And our gravitational force here, we'll use mg. So it's going to be 5 times 9.81, and you should get 49.05 newtons. 49.05 newtons. We also have this force acting on this object at an angle. Now we're going to note here that this force is at an angle. There should be x and y components to this object. I'm also going to make this 49 negative to show that it's downwards. Let's break down these components here of this 40 Newton force. We have a y component, and we have an x component. Well, how do we break down an angled object into x and y components? You might remember from our work on projectile motion, we're going to use sine and cosine. In this case, the Fy is f sine of theta. So it's going to be 40 newtons times the sine of 60 degrees. And if we actually calculate that, we should get 34.6 newtons. And if we work out Fx, which is going to be the f cosine of theta, we get 40 newtons times the cosine of 60 degrees, and that is going to be 20 newtons. So now we have our two components, our Fy upwards and our Fx downwards. Let's look at what's actually happening to this object. I'm taking an object and we're pulling it along at an angle. We're going to pull this object along at an angle. What's actually going to happen? First of all, if I slightly push up on this object, like if I took, for example, a bag here that's at rest on a table, if I slightly pull up on this object, the table doesn't have to use as much force to support it. The table will still support it upwards, but it doesn't have to use as much force to support it. So while normally your normal force is equal to gravitational force, here your normal force is equal to your gravitational force minus the Fy, minus this y component here. So we get a normal force, which is equal to 49.05 newtons minus 34.6 newtons. And you should get a normal force, which is approximately 15 newtons. I did a little bit of rounding there. Ultimately, between this 15 newtons upwards and this 34.6 upwards and this negative 49.05 here, well, what is your y component of force going to be? Let's take a look at the net force on the y-axis, our net force on the y-axis. Well, we're going to have 34.6 upwards plus 15 newtons upwards minus 49.05 newtons upwards. And despite a little bit of rounding, you should get about 0 newtons. Should get 0 newtons of upwards and downwards force on this object. I'm pulling it at an angle, but it's not going to accelerate up or downwards. Which means this acceleration is only on the horizontal axis. So let's find our horizontal acceleration. Let's find our summation of forces on the x-axis. What forces are acting on the x-axis? We said assuming there is no friction, so the only force we have on the x-axis is this 20 Newton force. And that is very common here. Usually in a situation like this, your F net is going to simply be the force on the x-axis. Well, what was the force on the x-axis? We had calculated it. We did 40 times the cosine of 60. We got 20 newtons. So the Fx is 20 newtons. I take my 0 newtons on the y-axis and my 20 newtons on the x-axis, and I get the actual net force of the object, which is still, again, 20 newtons. So let's go back into our question. What is the acceleration on this object? Well, if I have a net force of 20 newtons, and we know F equals ma, 20 newton force, 5 kilogram mass, what is our acceleration? 4 meters per second squared. And that answers our first question. What is the acceleration on this object? It is 4 meters per second squared. This would be assuming that there's only one force acting on it, and really only the horizontal component actually accelerates it. And that's where this 20 newtons come from, because the horizontal component can be calculated using the force, 40, times the cosine of the angle, so 40 cosine 60. If you're not getting this 20 newton answer, you're probably in radians. Make sure you change your calculator to degrees. Let's go a little bit farther with this. I am actually going to erase some of this work, but we're adding a new thing here. If instead it had an acceleration of 3 meters per second squared, what friction force did it experience? First of all, force of friction is always opposite the direction of motion. Force of friction only slows objects down, so it's opposite the direction of motion. And our question is, okay, well, the acceleration is 3 meters per second squared. Let's go back into some of this information here. I'm going to erase a good bit of this. And let's say to ourselves, okay, well now we have a force of friction acting on this object. And we have an acceleration of 3 meters per second squared. If I have an acceleration of 3 meters per second squared and a mass of 5 kilograms, the first thing I could find here is my net force. And my net force, mass times acceleration, is going to be 5 kilograms times 3 meters per second squared. So we have 15 newtons as our net force. All forces are still balanced on the y-axis. Nothing changed on my y-axis. I only added an x-axis force. Our friction is on the x-axis. So let's look at our summation of forces on the x-axis. Well, I know I have a net force of 15 newtons. And we have a net force here on the x-axis, which is going to be equal to our Fx, which is part of the applied force, plus our force of friction. This Fx here, this summation of forces here, this should be 15 newtons. Our Fx is 20 newtons. So what does the friction force have to be to slow it down enough so that 20 newton force is not making it accelerate at 4 meters per second squared? Well, it should be negative 5 newtons to make this equation work. And so our force of friction here would be negative 5 newtons. If I said the magnitude of it, it would just be positive 5 newtons. By using your mass and acceleration, you could find your net force and then find other forces acting on this object, such as the friction force. This is how you work with an applied force on an angle. We're going to explore quite a few of these.